Hello, Professor Sargent here again to discuss with you section 7.7. We know that when we square any real number, we get something non-negative. So this equation, x squared equals -1, has no real solutions. And furthermore, we want to talk about the square root of -1. That's not a real number. However, in this video, we're going to find a new number, a non-real number, I, the imaginary unit, to be the principal square roots of -1. And this imaginary unit, again, it's not real. We're going to take the real number system and append this imaginary unit to create a new, larger number system, which can be used to analyze a variety of problems, such as solving any polynomial equation. And in this section, we're not going to do that. We're going to concentrate just on writing square roots of negative numbers and on the arithmetic of complex numbers. The using I to solve any polynomial equation, that'll come later. If a greater than 0 is a real number, we're going to define square roots of -a as I times the square root of a. Here's some examples. Square root of -9 we define as I times the square root of 9. And of course, we already know the square root of 9 is 3. So we have I times 3. However, we don't normally write it this way. We ordinarily place the coefficient, so to speak, in front. So we would write 3i. If we're going to simplify the square roots of -50, then by the definition, that would equal I times the square root of 50. Now 50 is not a perfect square, but using what we've developed in previous sections, we do know that there is a perfect square larger than 1 that is a factor of 50, specifically 25. So we split that up as 25 times 2 inside, and then use the product rule for radicals. We have I times the square root of 25 times the square root of 2, and we know that the square roots of 25 is 5, while we cannot do anything with simplifying square root of 2. Now, in this case, it gets a little bit interesting. Normally we write this as 5i times the square root of 2. You might say, well, that's different from what I had previously. Technically, we should be writing 5 times the square root of 2, and then I afterwards. However, that might make it look like we have if we write those two close, it might mean to some people, oh, do we have the I under the square root? No, we don't. This how would we talk about the square root of I, or the square root of 2i? doesn't mean anything at all. If it does, well, that's for later. And for now, rather than even get into this confusion, we're going to put the I in front of the radical. And here's one more example. We have the square roots of negative 121. Actually, let's go with the negative of the square root of negative 121. Those two negatives cannot get together. You've got that square root in the way. So if we apply the definition, we would have negative I times the square root of 121. And then 121 being a perfect square, it is square root of 121 is 11. We have negative I times 11, or negative 11I. We define complex numbers as A plus BI, where A and B are both real numbers. A is called the real part, and B is the imaginary. Now, if the imaginary part is 0, then we have a number that is purely real. And if A, the real part, is 0, then we have a number which is purely imaginary. Here's some examples. Negative 3 plus 5i. The real part is negative 3, and the imaginary part is 5. And we've got the marker sign out here, so we're going to switch. We take 13/3, then the real part is 13/3. And since we don't have something added to that with an I, the imaginary part is just 0. We have negative 7i. Well, there's no real part. We just have an imaginary part of negative 7. And if we have, say, 2 minus 9i, the real part is 2, and the imaginary part is 9. I want you to take note of the fact that in some other textbooks, the imaginary part would include the I. So in other textbooks, for this first example, they would say the imaginary part is 5i. On the second example, it would be 0i. Well, that's 0 times I, and 0 times I is still going to be 0, just like with a real number. 0 times something is 0. On the third example, we'd say that the imaginary part is negative 7i. And on the fourth example, we'd say that the imaginary part is negative 9i. That's for other textbooks, though. And for our textbook, we'll go with these answers. Before getting into performing operations of arithmetic with imaginary numbers, complex numbers, We have a little bit more to do with definitions. We're going to define a complex conjugate. The idea of a conjugate came up a little bit earlier in this chapter. Something similar is going on here. For a complex number a plus bi, complex conjugate of it is a minus bi. What we're doing here is we're changing the sign of the imaginary part. Only the sign of the imaginary part. So here's some examples of finding complex conjugates. We have 1/2 plus 3/2 I. It's complex conjugate. Just change the sign of the imaginary part. So its complex conjugate is 1/2 minus 3/2 I. If we have 3 minus 4i, then changing the sign of the imaginary part, well, that's already negative. So that negative is going to become positive. You get 3 plus 4i. If you wanted to get really technical here, looking at the way the definition is written, then you'd have to view this as 3 plus a negative 4i, and then its complex conjugate, you'd be taking 3 minus negative 4i. So again, just like with the reals, negative times negative is positive. And so we still get 3 plus 4i. In other words, it's extra work. Let's just talk about changing the sign of the imaginary part. If we have 107, there is no imaginary part. So its complex conjugate is just 107. Again, you could go through some extra stuff here and say, well, the imaginary part of 0 was negative 0. It's still 0. And so adding 0i to this, we're still going to have a 107. And as a final example of finding a complex conjugate, if we have negative 22i, it's a purely imaginary number, no real part. Changing the sign of that imaginary part, which is negative 22, change that to a positive 22. So complex conjugate is 22i. So now we're ready to talk about the arithmetic of complex numbers. Adding, subtracting, then multiplying, and finally dividing. Some of this is going to involve using implicitly the commutative, associative, and distributive properties. Those were properties that held true for the real numbers, and we're going to say that they hold true for the complex numbers as well. So with addition and subtraction, think of combining like terms. say we have to add -4 plus 5y to 2 minus 4y. Again, we're thinking about combining like terms. So we'll get together the -4 and the +2. And we'll get together the 5i and -4i. Technically, you could write it that way. Of course, -4 plus 2, that's -2. And technically, we talk about factoring out the I here. So 5 plus -4, that quantity times I. Of course, 5 plus -4, that's the same as 5 minus 4. So we have +1i. Well, when 1 is multiplied to something, we don't really need to write that, so we'll put -2 plus I. And then understood that we're talking about an imaginary part of +1. As for subtraction, say we have to subtract 7 minus 2i minus -1 minus 4i. You think of distributing the subtraction. Really, that subtraction would be the same as 7 minus 2i plus -1 times the quantity -1 minus 4i. And then we can distribute the -1. Well, again, we could write a little bit less. And just say 7 minus 2i, negative of -1, that can be +1. And the negative of -4i, that can be +4i. Get together the 7 and the 1, they're both positive, we have 8. And then -2i plus 4i, -2 plus 4 is 2, so 8 plus 2i. With multiplication, not only are we still going to be thinking about the commutative and associative properties and the distributive property, now we can be thinking about that shortcut of FOIL. Also, in case I forgot to mention it earlier, since we defined the principal square root of -1 to be I, so we square both sides, that gives us that I squared equals -1. So, we have to multiply 6i times 2 minus 4i. We're going to distribute 6i to the two terms inside. 6i times 2 minus 6i times 4i. Again, implied in this, we're going to get the 6 and 2 together in front of I. Multiplying 6 times 2, we have 12i. We use the commutative property to get the second term, 6 and 4 together. 6 times 4 is 24. And just like with real numbers, when you're multiplying two things, the same base, we're going to have I times I is I squared. Here's where we use what we just stated here. I squared is -1. So that 24 times I squared times -1. Think of that as -24 times -1. Two negatives and a positive. And we're getting something here that is saying we've multiplied two complex numbers. We're getting something that is a complex number. We're going to write it in that a plus bi form. That's the standard form of a complex number. So using the commutative property of addition, 24 plus 12i. Say we have to multiply 6 minus 2i times 4 plus I. Here's what we can just split. Because this complex number, a plus bi form, you can think of those as having two terms in each of those. So we're going to have 6 times 4 plus 6 times I minus 2i times 4 minus 2i times I. 6 times 4 is 24 plus 6i. Get the 2 and the 4 together here, minus 8i. Get the I and the I together here, minus 2i squared. 6i minus 8i is going to give us minus 2i. Again, I squared being -1. -2 times -1, that will give us a positive 2. Then we can say, oh, we've got two parts that are purely real, 24 and 2. Let's bring them together. 24 plus 2 is 26. So that bit of using I squared equals -1, again, is allowing us to write complex number times a complex number is a complex number. We have it in the standard form. And finally, for multiplication, let's multiply 3 minus 4i times 3 plus 4i. By FOIL, 3 times 3 plus 3 times 4i minus 4i times 3 minus 4i times 4i. Three times 3 is 9. 3 times 4i is 12i, and that's being added. 4i times 3 is also 12i, but that's being subtracted. And then 4i times 4i being subtracted, you're going to have 16i squared. Our 12i minus 12i, that's going to cancel out. And the I squared can be replaced with a -1. A -16 times a -1, that's going to give us positive 16. So 9 plus 16 is 25. You may notice that we're multiplying two numbers that were complex conjugates of each other. And we got something that was purely real, 25. It's not coincidental. That will always happen when we multiply complex conjugates. Also, we could have made this easier. This appears to fit the difference of two squares form. A minus b, that quantity times the quantity a plus b. And the order could be reversed. We could have the quantity a plus b times the quantity a minus b. That's going to equal a squared minus b squared. So we could have simply taken 3 squared minus 4i, all of that squared. 3 squared is 9, minus, and I'm going to apply our one of our power rules that we have for real numbers that will apply here as well. And I'm squaring the two factors of both the 4 and the I. It's going to be 9 minus 16 I squared. That's what we wound up having here, 9 minus 16 I squared. We got 25 that way as well. You may find using the difference of two squares form when you're multiplying two complex conjugates simpler to work with. Okay, now division. Quotients with complex denominators are simplified by finding the complex conjugate of the denominator and multiplying the numerator and the denominator by the complex conjugate of the denominator. So, really what we're doing is rationalizing the denominator as in section 7.5. Remember where you see I, you have I is squared of -1. This is going to allow us to write the answer in the standard form of a complex number, a plus bi. It's like we did with multiplication. Now, if we have 1 plus 2i divided by 3i, the complex conjugate of 3i, since that's purely imaginary, is going to be negative 3i. In the numerator, we will distribute that negative 3i because we're multiplying the top and bottom by the conjugate of the denominator, and the entire numerator is 1 plus 2i, so we're going to have to distribute. 1 times negative 3i plus 2i times negative 3i. We'll simplify that in a moment. In the denominator, 3i times negative 3i. It's going to be 3 times negative 3 is negative 9. And I times I squared. And we're going to be able to use I squared as -1 there. Also, we're going to be able to use it up in the numerator momentarily. So, negative 3i plus 2 times negative 3, that's negative 6i. All right, plus a negative as subtraction. So we've got the numerator, negative 3i minus 6i squared, all over negative 9i squared. Where we have the I squared, put in -1. Being multiplied. So in the numerator we've got negative 3i, multiplying these two, negative 6 times negative 1, plus 6. And in the denominator, negative 9 times negative 1, you get positive 9. Putting the numerator in standard form of a complex number, 6 minus 3i over 9. And that looks pretty good. But we may sometimes need to go a little further here to see it rated as a complex number. You can divide the top and bottom by 9. Sorry. You can distribute that division of 9 to those two terms. And reduce. 6 9ths reduces to 2/3. 3 9ths reduces to 1/3. So 2/3 minus 1/3 I. Dividing a complex number by a complex number, as long as that complex number is not 0, it's going to give us a complex number. Continuing with division, say we have to divide 4 over 3 minus 5i. The complex conjugate of the denominator, we've got 3 minus 5i in the denominator. This complex conjugate is 3 plus 5i. So we multiply top and bottom by 3 plus 5i. In the numerator, we're going to distribute to 4. 4 times 3 plus 4 times 5i. And in the denominator, I'm going to use what I mentioned at the end of doing multiplication to make things go a little quicker. I'm going to use the difference of 2 squares. You could do FOIL instead and get the same thing. So in the denominator, I'm going to have 3 squared minus all of 5i squared. 4 times 3 is 12. 4 times 5 is 20. So we've got 12 plus 20i in the numerator. In the denominator, 3 squared, that's 9. The square root of 5 and the I, both of those factors. So 12 plus 20i in the numerator still. Over 9 minus 25i squared. Replacing the multiplication by I squared with multiplication by -1. Then negative 25 times -1, that's plus 25. Nine plus 25, that's 34. Again, we can distribute that division by 34. And where we can reduce. We can use the fact that these two numerators are even, and that 34 is even. Running top and bottom by 2. Got 6 over 17 for the first one. That's as far as that will reduce. And similarly, 20 over 34, dividing top and bottom by 2, that will reduce to 10/17. So that's as far as that's going to reduce. 6/17 plus 10/17 times I. Again, we're seeing complex number. Even 4, though it's purely real, it's also a complex number. Complex number divided by complex number is a complex number. So we're not dividing by 0. As a final example for division, say we have divide 3 plus I over 4 plus 2I. The complex conjugate of the denominator, switching the sign of just the imaginary part, we multiply top and bottom by 4 minus 2I. So we're going to do FOIL in the numerator. Times 4 minus 3 times 2I plus I times 4 minus I times 2I in the denominator. Again, we can do FOIL to multiply the two conjugates of each other, but I'm going to speed that up by the difference of 2 squares. We're going to have 4 squared minus all of 2I squared. The numerator, 3 times 4 is 12. 3 times 2I is subtracted, got minus 6I. I times 4, I'll write that as 4 times I. I times 2I, this is being subtracted, is 2I squared. Do more to simplify that in a moment. In the denominator, 4 squared is 16. Minus, I'm going to distribute the squaring to both factors, the 2 and the I, both getting squared. More simplification on that momentarily. Minus 6I plus 4I. Minus 2I. Replace the I squared here with what's being multiplied. Replace that with multiplying by -1. Denominator, square root of 2. I squared, we multiply to that. Replace that with multiplying by -1. Doing the multiplication by -1 in both the numerator and denominator. Combining the like terms, real parts. And then distributing that division by 20. Reducing where we can. Top and bottom by 2 into these. We've got 7/10. That's 1/10 times I. As a final topic, we're going to talk about Powerslide. Really, this is a special case of multiplication, but remember that when we define I to be the principal square root of -1, when we square both sides, forget I squared equals -1. Well, if we take that further, I cubed, well, cubing same as 1 over cube I. That's the same as multiplying I squared times I to the first, which is I. And we've already said that I squared is -1. So -1 times I, or just -I. I to the fourth, do that same split up, split one of those off. I to the fourth is I cubed times I. We just said that I cubed is -I. So -I times I. It's -I times I squared. I squared is -1, but we've got another negative in front of that. The negative of -1 will cancel out, and we've got +1. Finally, I to the fifth, split one of those factors off. I to the fifth is the same as I to the fourth times I. I to the fourth, we just figured out, is 1. So 1 times I is I. I to the fifth is equal to I. I.e., I to the first. Notice that those are 4 parts. And we figured out I to the fourth was the purely real number, 1. What's going to happen here is every fourth power go back where you were. Select the clock. Set 12 hours or 4 hours. So every integer power of I can be written as either I, -1, -I, or 1. We can use that to simplify for an example. We have to simplify I to the 11. 2 ways we can write this. I to the fourth is 1, that's key. 4 goes into 11 twice. 4 times 3 is 8. 11 minus 8 is 3. We've got 2 remainder 3. Short version of the story here is going to be that I to the 11 equals I cubed. And I cubed equals -I. Now we could be a bit pickier, write out a bit more here. Write that 11 as 4 times 2 plus 3. Split up the addition of the exponent. As multiplication of things to the same base. And then use one of our power rules for exponents. Using it for real numbers. Use them for powers of I. Now what I'm looking at here are powers of I that are 1, 2, 3, or 4. We've got I to the fourth here, I to the here. So I to the fourth is 1. 1 squared. I to the cube. I to the third, or I cubed, is -I. 1 squared is 1. 1 times -I is just going to be -I. Same result either way. This is really breaking it down, but this may be sufficient for some. So you have to simplify I to the 96th. Short approach here. How many times does 4 going to 96? Into 9 twice. 4 times 3 is 8. 9 minus 8 is 1. Going down to 6. 4 goes into 16. 4 times. 4 times 4 is 16, so there's no remainder. I to the 96 is equal to I to the 0. Just like with real numbers. As long as it's not 0 to the 0, anything else to the 0 power is 1. And for our last example, simplify I to the negative 3. One approach, again, same as when we're working with real numbers. You have a negative integer as an exponent. We write I to the negative 3 as 1 over I to the positive 3. I to the third we have is negative I. Then we can apply what we were doing just a few minutes ago. Multiply top and bottom by the complex conjugate of the denominator. So that's negative I, multiply top and bottom by positive I. The numerator 1 times I is I. Denominator, negative I times I is negative I squared. I squared is negative 1. We've got negative I squared. And the negative of negative 1 is 1. Dividing something by 1 gives you that something that we were dividing into. So, just I. That's all for this section and all for this chapter. Thank you.